All right, and so now at this point, anyone viewing this video is ready to face a little bit more of a challenge. Okay, so now let me bring it up, and we're gonna set that into an actual example to continue from our past examples here. But so I recall, or any of us here can recall from earlier video lecture of mine where I was still going over the Riemann sum, okay? And earlier part of this video, I already mentioned that back to this motivating problem here, the whole motivating problem that created all that, the process about taking the Riemann sum and all that. Let's say the x squared function, okay? The x squared function famously has that parabolic shape right here, and now in the from 0 to 1, I begin that problem as an area problem, okay? And so, and then I explained about how the Riemann sum came to the idea of the definite integral from 0 to 1 of x squared dx, and that would give us the exact area. And so it's time to really get into it. Now, I said earlier, this area in some of the earlier video lecture, I did say clearly that I knew the answer was a 1/3. And then as a matter of fact, it's just the earlier part of this particular topic, indefinite integral, I talked about. I said that this area underneath this curve, this parabolic shape right here between the x-axis and the curve, and then inside of the interval from 0 to 1, that area is a 1/2. Okay, but then when I stated it there, that was all I said. I could not give any reasoning. I could not give any explanation why, and I used that as a destination to point out that we gotta take infinitely many subintervals and accumulating it to eventually arrive at that. Okay, so when we allowed our Riemann sum to reach infinitely many subintervals, and then that will consequently produce infinitely many rectangles in here, and those become the stripes, and that gets us a 1/3. But now let's really face that challenge to really see the process of how we're doing. And so now allow me to reuse this problem, but we really are going to tear it down and calculate that, and that's the challenge I was introducing earlier. Okay, so now I'm calling that now example 4. Let's really evaluate, okay, the integral, the definite integral from 0 to 1 on this function x squared. We want to find the definite integral in respect to x, okay? And this is not a problem where we try to imagine or we try to visualize that as the area of some special graph. It's not a circle. It's definitely not a trapezoid. It's definitely not a triangle or anything like that. And you already saw that if we're visualizing this integral here as an area, if we're interpreting this integral as an area, it is an irregular, very irregular shape here. Okay? And so in that way, the only choice for us. So now allow me to continue the instruction of this example. I would like to evaluate this, okay, using the limits, okay, definition. Okay, so what exactly is the limit definition? So now be careful with the way how we use terminology. Now up to this point, now back in your differential calculus, there was also a time that we used the name the limit definition, because the concept of derivative also use limit. And now when we go to the integral calculus, where we accumulating areas, it is another limit process. And so ultimately, this limit definition here, I refer to the Riemann sum, okay? That famous Riemann sum, setting up the Riemann sum work, and then take the limits as the number of subintervals increase to infinity, positive infinity. And that's what the limit definition is. Okay, and so that's the goal here. We do want to get to the precise answer, and as I stated before, we already had an answer knowing it's 1/3. But now how do we find that 1/3? Let's use the limit definition. Okay, It's an unavoidable thing right there. Eventually, anyone taking calculus in a formal calculus course, that to make your way ready for a math-related career or a technical major right there, you have to at least go through this problem here, this challenge here, once or at least twice. At least once or twice. Okay? Now, I have to also admit, it's an unavoidable thing, because eventually we will learn a much better technique to get things done a lot more effectively. But at this point here, we got to face some challenge so that later on, when we learn a much better technique to calculate this problem right here, we can appreciate how much work and how much effort the past mathematician have come up for us here. Okay, and so now clearly as a goal, we want to find this area. Okay, using the limit definition. And the area here, let me write it small because I need more space right here. The area between the curve for x squared and inside of the interval from 0 to 1. Okay, this area, how can this be 1/3? So that's nothing but just to really fire up the evaluation work right here. And we have to go through the limit definition. Okay, and so now I spoke a little while ago, back in the earlier part of the lecture, that now let me get on the board, the other board here. So for any integral, okay, an integral from a to b, a definite integral from a to b, is a Riemann sum, where first of all we break our delta x into, we break our interval from a to b into n subintervals, and then the delta x is the width obtained by b minus a divided by n. And so in each subinterval, we pick a chosen point c sub I and we multiply that with the delta x. And we have been visualizing that as the area of one rectangle at the ith and at any particular ith interval. Okay? And so that was the general idea right there. And then we took the limits, allowing n to increase to infinity. And then that's Riemann sum was a summation that runs from 1 to n. So this was the general limit definition. But then when we actually get into that, I also explained that, I also had a note earlier that, so because this ci right here, this ci means it's a chosen value. Okay, it's a chosen x value. Keep that in mind again, chosen x value in the ith interval. Okay, so I need to constantly remind people on that. It's in any ith interval. So chosen, that's why back when I was going through the Riemann sum and the left Riemann sum and the right Riemann sum, and I also discussed about the midpoint. So those are all just different choices. Those are all just different choices. So that chosen x value could be, we can run with the left endpoint rule or the right endpoint rule, or with the midpoint rule. Okay, and that's what the chosen point here is all about. So in this particular problem, allowed me to use, my plan here is to use, I use left Riemann sum. Okay, I use the left Riemann sum. Okay, and then outside of this example, if any of you following with this video lesson want to get successful with your learning right here, I highly recommend that you can restart the whole process here, but using the right Riemann sum. Okay, and also use the midpoint Riemann sum right there, so that you will get even more experience of handling this evaluation problem using the limit definition. Okay, and so now I'm again going to swing over to my other board, and let's also recall what it means by this, from this general Riemann sum. What does it mean by using the left endpoint? And that's why I was writing down this word also, and kind of getting it hanging there. So that also means this integral right here can equal, if we are now going with the left Riemann sum, okay, then the integral from 0 to 1 for our function here, for any function f of x dx, okay, can be can be started as a Riemann sum where in each interval, in each I interval, we're going to pick the left endpoint. Okay, we're going to pick the left endpoint, and then again, delta x is permanently defined as the difference b minus a, and divided by n, the number of subintervals desired. Okay, and so we're going to multiply that with delta x, and then we're summing up from the first rectangle to the nth rectangle, and we're going to allow, as a limit process, we're going to allow the number of subintervals to increase to infinity. And so now that's the plan right here. We're going to use this, and so the same integral right here, the same integral. Okay, and I noticed I used the incorrect. It's supposedly just some general a to b right there. So the same integral, the same definite integral, that is a choice, and it will get us the same exact answer, or somebody else can go with the right endpoint. In this particular example, I plan to stay with the left Riemann sum. Okay, all right, and so now one more time before so now I need to erase this board, even though I wrote it here not too long ago. Okay, because I need to prepare some other information. So here's what we can do in terms of going with the left endpoint right here. So I recommended this habit from earlier part of the video lecture and even in the earlier lecture on Riemann sum, but let's say in an interval generally from a to b. Okay, generally from a to b, then we try to imagine the intervals, the subintervals that we partitioned into. And so now, particularly in this problem, our interval is from 0 to 1. Here's the interval from 0 to 1. And there can be many more intervals after this. But see, this is interval number 1. And allow me to write in red ink right here. This is interval number 1, number 2, number 3, and there are many more. Okay? And so, generally speaking, in our problem, and since we are in this problem here, since we're about to use a Riemann sum, then delta x in our particular problem, recall that this function here is the x squared, and we are accumulating from 0 to 1. So our total interval is from 0 to 1. Okay, and then so now to set up the Riemann sum, this is the plan right here. Each delta x has to be 1 minus 0 over n. So we just start out with some general number of n subintervals. It could be 4, it could be 5, but the idea is we start out setting up with some general n number of subintervals. And that's why I have interval 1, interval 2, interval 3, and however many more. I'm leaving that just sort of like an open end right there. Okay, but all of these intervals are fitted, all of these subintervals are supposed to be equally fitted in that total interval from 0 to 1. That's why this delta x is a 1 minus 0, the ending point of our total interval, minus 0 over n. Okay, and so consequently delta x will equals 1 over n. So think about it. If we back from the beginning Riemann sum problem that I introduced, and if we stay with 4 subintervals, then delta x is a 1/4. Okay, if we stay with 100 subintervals, then delta x would be 1 over 100. Okay, it all depends. But now, generally speaking, at any number of subintervals, designated number of subintervals, then each delta x here, each space here is a space. So each of these here is a 1 over n space, a 1 over n space. Okay, so 1 here come out because it's a total difference between 0 and 1, but over n because we have n subintervals. Okay, and so now in that way, let's regulate, and everything I'm doing right now is still consider as scratch work level right there. Okay, but now at least this part right here can be placed in the formal amount of formal steps. So formally, when you're writing up your steps right here, anytime that you're performing an evaluation of a definite integral using the limit definition, you can always start out by showing the calculation for your delta x. Okay, so in your Riemann sum, you will need the delta x. So delta x here is See, 1 over minus 0 over n, and we generally come up with delta x. Each delta x here equals a 1 over n. Okay, so now back on my other board where I was still performing the scratch work. So think about this. We're using, again, I'm reminding, we are using the left Riemann sum, or specifically in each interval here, I'm looking at the left endpoint. So in this first interval, my x1, first interval, but left endpoint. So left endpoint on the first interval is going to be 0. Okay? And then left endpoint, but on the second interval is going to be 0 because that's the starting point here, but plus a delta x over plus 1 space of the delta x. Okay, delta x currently equals 1 over n, but the generalization I would like to point out is, so for second interval, the left endpoint would be the starting point, okay, plus a delta x over. Okay, so I'm kind of halfway mixing between a generalized case and the case that's specifically for our problem. So generally, when we're looking at a total interval from A to B right here, okay, and there are a whole bunch of sub-intervals, and how many more? Okay, then this is going to be, this space here is a B minus A over n. That's your delta x. But then in the first interval, see, for interval 1, interval 2, interval 3, and there are many more intervals, sub-intervals, then the first left endpoint, okay, the left endpoint on the first sub-interval is just the A value, which is like how I had that 0 over here for the XL1 right here, the left endpoint on the first interval, okay, and actually I shouldn't have that sub-0 right there. There's no reason to have the sub-0 there. And then x, the left endpoint on the second interval is the starting point, but we're gonna add, because the next left endpoint is here. So for interval 2, but left endpoint is there, so it's A. But we plus with 1 time of the delta x. See, that delta x is the space right here. So we add 1 point over. Okay, and so then moving on to the next one. On the third interval, left endpoint will be from the starting point of our interval. We're going to add 1 and 2 times of the delta x over. So plus 2 times the delta x. So just like that, in our specific problem, for the third left endpoint, or the left endpoint on the third interval, this is the starting point plus 2 times of the delta x. Okay? And then, so now in a general case, when we move on to the left endpoint on the fourth interval, it is supposedly, so this is our first left endpoint, this is our second left endpoint, this is our third left endpoint, so this is our fourth left endpoint right there. Excuse me. And so now that means the left endpoint on the fourth interval has to be from where our starting of the total interval, we're going to add with 3 times of the delta x. Okay, 3 times of the delta x. So now similarly, right here in our particular problem, so when we reach to the left endpoint on our fourth interval, starting point is 0, but plus 3 times of our current delta x value being a 1 over n here in our specific problem. Okay, so now we are ready to see a regulation, a general regulation. Have a close observation of this. When we're at the third interval, when we're in the third sub-interval, the left endpoint is the very beginning starting point of the total interval, but plus 2 times. So the number 2 here is 1 less than the current interval that we're in, the current interval position, the current sub-interval position. So it's interval 3, but we need to add 2 times of the delta x from our starting of the total interval. Okay, and then so now, see, and again, let's double check again when we're at the fourth interval. If we are currently at the fourth interval, then we need to add 3 times of the delta x from our starting point, 1, 2, and 3, to get to the left endpoint on the fourth interval. And so now it gets us into a regulation, a rule. So that means generally at any ith, okay, at any ith interval, the left endpoint will be obtained by the starting point A plus, and just now I realize I need more space in that. So at any ith interval, the left endpoint will be the A value, the very beginning point of our general interval. Okay, plus, but I minus 1 time. I minus 1 time. Always 1 less than the current position of your interval, and multiply with delta x. Okay? And so now again, so now in that case right here, for our problem, generally, particularly into our problem right here, then when we're at any general ith interval, in our problem, particular problem where it's from 0 to 1 on our interval, then this is going to be 0 plus some I minus 1 times delta x. That's what it is for our problem like that. Okay, 0 is the starting point of the total interval, of the overall interval, and then the delta x here is that value, and then it's always I minus 1 less than the current interval, sub-interval position that we're at. Yeah. Okay, so the generality that I have pointed out now is, I wrote it down here, but allowed me to write it in some other more open space so it can catch people's attention a little better. So at any ith interval, in a general case, okay, then the left endpoint can be found by the starting point of your total interval plus I minus 1 times the delta x. Okay, and the delta x is always of course always, I had it written down, but I had to erase it. It's always, and it's actually right here. Okay, it's always b minus a over n. That's generally how we found our delta x. Okay, and so now in that case right here, now let's specifically narrow our attention into this particular problem of ours. We got a general regulation of how to create, come up with, generalize the left endpoint at any ith interval. And so now in our particular problem, when we reach to any of our ith interval, the left endpoint would be as following. The left endpoint is going to be I minus 1, because 0 plus anything is just that quantity itself, I minus 1 times. But now our delta x in this specific problem is going to be 1 over n. That's our general regulation for this particular problem where the interval is going from 0 to 1. If our integration limits go from 0 to 1. Okay? So why is it 0 to 1? Again, maybe we have gone far enough that some people might lose the focus, but the 0 to 1 is because we're looking at this integral limit right here. Low is at 0 and ending of the accumulation at 1. The accumulation start at 0, ending at 1. Okay? And so now, again, that's what I have just found. So in this specific interval, right? In this specific interval from 0 to 1, then to reach the left endpoint at any ith subinterval, that is going to be I minus 1 multiplied with 1 over n, because 1 over n is going to be our delta x in this case, and I already wrote it down earlier. So now with this formula right here, we can shorten it down a little further. So in other words, the left endpoint at any of our ith subinterval can be written as I minus 1 over n. So that's making it a little shorter. Okay, that's making it a little shorter to write in terms of the expression instead of the lengthy one like this. And so now I can write this. So all this here is just the reasoning. I can write this into my formal step. So once we know our delta x, right, then at the ith interval, okay, at any ith interval, then our left endpoint on the ith interval is going to be determined by I minus 1 over n. That's what it is. Okay, and so now we have almost all of that information. And so now again, I'm going to swing back to the other board erase out all of these scratch work that, listed down my reasoning, my thought process. And now this is what I'm doing. Now we're going to put all of those pieces into the Riemann sum formula, the left endpoint, the left Riemann sum. Okay, and so now this specific integral from 0 to 1 of the x squared function is accumulation. We're accumulating things that start out as a Riemann sum with some general n number of subintervals, and then we're going to keep increasing the number of subintervals. And so in that way, at the very start, I'm setting this up as a Riemann sum. Okay, it's going to be, yes, f of x times generally any left endpoint of any ith subintervals and multiply with delta x, okay, where I is from 1 to n, and then we take the limits where n increased to infinity. This is always the famous left Riemann sum that we're writing it down. So any integral will equal to that general setup. Okay, but now in our specific problem, the integral is from 0 to 1. So delta x, we already knew that delta x. So in this sum right here, it's a limit, okay, to infinity. And then I is going from 1 to n. But allow me to leave this part empty a little bit. But the delta x now, we already knew it's a 1 over n. So I'm going to substitute that value into my delta x. 1 over n, substitute for my x. Because we found it right here. We found it right here. And we listed it down. And I gave so much explanations earlier. And so now our function in particular is the x squared function. So now at any x of I, at any left end, at any interval, the x of L, the left endpoint has to be squared. So it's going to be x of xl, the left endpoint at the ith interval being squared. So the reason I have the square here is because, see, it's the left endpoint at the ith interval being into our function. Our function is the x squared function, and that's why I'm squaring that. Okay, and so now one more step further. We knew that in this current sum right here, we knew that each of the left endpoint at any ith interval can generally be written as an I minus 1 over n. And so now in our function it's square. We're multiplying that with a 1 over n. Okay? And so now at this point, it is extremely important that if you haven't watched my earlier videos on how to operate and how to get comfortable with the summation notation, I highly recommend pause the video here or even exit out of the video, go back to my other video lesson that I introduced the kind of problem that gets you comfortable with this kind of work right here. Okay, so practice with your skill from that earlier video there when you specifically working on summation notation, where I try to break it down and focus only on summation notation, and then come back to this video. Okay. And so now in this video here, allow me to move on with the assumption that you have already viewed my other videos or have had or already experienced to manipulate with a summation like this. And as I said, summation is not an easy work to handle. It's a challenge, and the challenge is right here. Okay, and so now assuming you already had some experience with summation notation, then in this summation now, in the way how I see it, 1 over n is the part that's independent with the ith position. Okay, now we're thinking strictly in terms of a summation. Then the 1 over n components here, even though it's a variable, but this variable is independent with the term position. And so in other words, I can treat that simply as a common factor or a coefficient can be placed in front of my summation. And once again, all of that explanation can be explained in my other video lesson when I was specifically showing the skills to work around and to operate with summation notations. Okay, and so that means in the next step, here's how I'm seeing it. Even though here is the whole term, but the term already has that part, and it's a multiplication right there. So it's already had that part being independent with the ith position, and that's what I was trying to explain earlier. So now in my next step, I can write the 1 over n in front. of the summation. Okay, and the space here is getting a little too tight right now. So it's a limit problem. Okay, and I'm not doing anywhere near the limit work yet. It's just I'm operating and manipulating around with the summation right here. So 1 over n times the summation of, and what's remained in the summation now is a 1 minus I over n all square. Okay, summing from 1 to n. Okay, and so now even further, that as a little scratch work, okay, in a little margin of my board here, I minus 1, or how about I minus 1 all over n square, that part right here algebraically equals to I minus 1 all square over an n square. Over an n square. Okay, so acknowledging this right here, knowing that fact right there, I am going to use that algebraic understanding into my current summation. And so it's a 1 over n times the summation of, so that's, I can rewrite it as I minus 1 all square and times 1 over n square again. Okay, and of course allow me to explain a little further. But so earlier I wrote I minus 1 over n all square is to equal I minus 1 all square over n square. Algebraically I can also rewrite that as I minus 1 all square times 1 over n square. It's just another algebra thing. You, at this point, you cannot blame any of your instructor to ask you to be fluent with algebra in order to absorb these problems right here. Okay, so when you're at a calculus level, you are of course must be mature enough in algebra so that you can learn fluently with these. So it is highly recommended that you review any of your algebra skill if you're still feeling shaky with any of these skills right here. Okay, and so now it's a summation from I to 1 to n, and then still it's a limit problem where we're allowing the limit n goes to infinity. Okay, and so now I need to leave all the work here and then move on to my other board. So now on my other board, okay, so continuing from the next step. Now from the earlier very last step I had right here, then you can notice again, just in that same argument I've made, again in my current summation, the 1 over n square is once again another part that is independent with the I index position of each of your subintervals. Or in other words, this 1 over n square is independent. It will always remain 1 over n square for every term. 1 over n square multiplied with this square right here in every term of your summation. So in other words, we can pull that in front together with this 1 over n. Okay, because you see that earlier I spent so much time explaining all of that algebra because I want to explain that we can extract out that independent part further, and that independent part right here can be brought in front again. And of course I'm going through this problem in the slowest pace as I could. Forgive me on that. If you, in case you are already a lot more fluent in algebra than how I assumed, then feel free to speed up your own process like that. But allow me to explain that in the level where some people are still, have some other algebra. Some viewers to this video lesson are still being a little shaky in your algebra. And so now with that independent part, I'm pulling it out front again and combine that together with this 1 over n factor. So that is the reason why in my next step I'm going to produce the following. It's a 1 over n cubed as a total factor right there, as an overall factor, and multiply with the independent, multiply with the summation in the form of an I minus 1 all square. Okay, and summing from I equals 1 to n, and this is a limit problem allowing n to infinity. Okay, so at this point there isn't any further independence part. There isn't any further part that's independent with the I. So everything that remains here is dependent on the ith position. And so we can't manipulate any further. And then we're going to start doing things differently. But now let me hit back to the other board right there and explain and kind of recap a couple of things. So I have that 1 over n here simply because that came out from delta x. Okay, and so that explained for that. And then I spent so much time explaining, I mean, the reason I had the square here because our function here is a square. It's a squaring function. And so we're supposed to pick, substitute the chosen point, in this case right here, the left endpoint on each interval into our function. And that's how our function is square. So I square every left endpoint at any ith interval. And so now in the next step down, see the 1 over I still stay the same. That's our delta x. That's our delta x. But our function at the left endpoint is now going to be I minus 1 over n all squared. That's how I had that. Okay, and then I keep working on the algebra to pull down all of that, all of those part I call the independent part, the part that's independent with the ith position of your summation. Okay, and so now we are ready to start picking up pace right here. And so now in my next step, I'm seeing that, and it's still a limit problem. We didn't do anything with the limits yet. The 1 over n cubed is the part that's independent with the I. We completely brought up front everything that's independent with the I position already. And so now this perfect square, we can FOIL that out. Okay, so your term here is an I square minus 2I plus 1 after FOILing out that square right there. All right. And summing our summation from n to equals 1 to, from I equals 1 to n. Okay, and so now anyone can review my earlier video lecture about how I manipulate with, and I had example problems very similar to something like this. So now in our term of the summation, our term has multiple terms in it. And so now that means we can break it down even further. So now it's a limit problem still, okay, because we didn't take any limit work yet. So 1 over n cubed is still here, but now we can produce 3 separate, or how about allow me to do the following. It's 3 separate limits work here, 3 separate sums. I squared is one of them, okay, summing from 1 to n, and then minus, it's another limit problem here where for the middle term here is a 2i, okay, where I, and then we also need to multiply with the 1/3, 1 over n cubed. And taking that limit, or actually we can just to save space, I'll just do it all in a 1 parentheses like that. Okay, and then there's a 1 over n cubed times the summation from 1 to n for the 1. Okay, and so now again, if you need a more detailed explanation of how I broke this down, I highly recommend to go view my earlier video lesson on how we can operate with the summation notation that had examples very similar to this particular one, and so you will understand a little better. Okay, and so now this summation, just aside from that 1 over n cubed, this summation is broken down into the summation of I squared, the summation of 2i, the summation of 1, and then I distributed that to 1 over n cubed for each term, and that's how I consequently ended up with this. And so that 2 right here can also be brought in front, because the 2 here now is, in this particular summation, it's a constant coefficient, and so I can also bring that. So instead of writing it as a next step, how about I'll just do this? So it's an I, and it's 2 times. Okay. So forgive me for the instant changing, the change right at the scene right there, right on scene. But now at this point, yes, it's still a limit problem, letting n growing to infinity. But now we have learned, we have spent, and that's why it is now extremely important that you have seen that other video lesson of mine where I showed how to manipulate with all of these. I squared is the specific summation on I squared right here. Okay, gives me n times n plus 1 times 2n plus 1, but over 6. Just that here is the final expression in terms of n. Okay, and so if you, once again, if you're not familiar with that term right there, it's a final expression of this summation of this I squared summation in terms of n. Then go ahead. If you're not familiar with that term, view my other videos. But it's now 1 multiplied with 1 over n cubed in front. Okay, minus. And so we're done with the first sum, and including with that 1 over n cubed right here, and everything now is expressed in terms of the n variable. And so now it's this summation on the I term right here is n times n plus 1 over 2. And if anyone wonder how I got that, view my other video lessons on that. Okay, and then we need to multiply with the extra factor 2 over n cubed. Okay, and then with this last one right here, it is the summation on this 1 right here, on this summation of order term 1, it's going to give me n. Okay, because n times 1. Okay, but then we need to multiply with the 1 over n cubed. Okay, so now what we have done here is we have re-expressed all of our summations into the final expression individually for each of the sum here, the final expressions in terms of the n variable, because n variable is the one that we want to take the limits to infinity. Okay, so now some algebra can kick in right here. Some algebra is going to start kicking in. You see the n cubed cancel with that n right here, and it will give me first term becomes so first term here becomes an n plus 1 times 2n plus 1, but over 6n squared. Okay. Second term has that 2 cancel with the 2 here, the n cubed cancel with the n, and that gives me an n squared, so it gives me n plus 1 over 2n squared. Okay, and the last term here gave me, see, 1 cancel with n cubed, right? I mean n cancel with n cubed, that gives me a 1 over n squared right there. So now we have a final expression in terms completely in terms of n. You also have your choice, you make common denominator and bring it all into one fraction, but I don't think there is a good need for that. Okay, and now we are ready for taking the limit. Okay, so at this point we need to bring in our experience from differential calculus, especially the skill in taking limits at infinity, to handle this problem. So good news is that each of these terms here is a rational expression. So we've learned from calculus 1, we've learned from the differential calculus that anytime we're taking the limit to infinity on rational function, then you see the first term here, highest degree in the numerator, is going to be a square. Because think about, if we really FOIL out all this, it's going to be a square. And the coefficient at the highest term here is going to be a 2. The coefficient at the highest power, as the highest degree there, is going to be a 2, because n times 2n is 2n squared. And then in the denominator we got a 2n squared as well. So numerator and denominator in the first term here has the same power. And so that means when we take the limit on the first term, and of course limit laws here apply, here. So the first term, okay, gives me a 2 over 6. That's the first term. Okay. The second term here, the rational function again, polynomial over polynomial, but the top polynomial on top is only degree 1. Polynomial at the denominator is degree 2. So that gives me a 0 for that one. Okay, and the last one is a similar case right here. It's a constant on top, but that means it's a polynomial of degree 0, degree 2 in the denominators in the denominator. So taking that limits to infinity is going to give me this last term right here to be a 0. All right, so now what have we found? I'm going to swing to my other board, take out some steps right here. But from all of that work, that we have done, then we have come down to just 2/6, and 2/6 is reduced down to 1/3. And so that means, now I never had enough space for this kind of problem, so I had to erase up a lot of work. So you can roll back or rewind the video here, but now what we have seen here is that after setting up this definite integral as a Riemann sum, okay, as a Riemann sum, and taking the limits for, and I particularly chose the left endpoint on any I subinterval and multiply with delta x. That's our basic starting point right there, our start point, okay, and letting n go to infinity. But after all so many steps of the work right here, we came down to 1/3. We came down to 1/3. So in other words, our final conclusion here is this integral. Now anyone seeing this video and connecting that with the earlier lectures that I have delivered for the integral calculus, then since our beginning day, I already said this answer is 1/3. And now we have found and we have proven it ourselves right here. Okay, and so that is our example number 4. It really is a challenge to use the Riemann sum, but it's doable. It's something that we can go through right there. Okay. All right, and so after that example 4 that I was doing, now it's time to set a general rule for left endpoint or right endpoint, okay? So that in case we decide to use any of these for our limit work to find an actual definite integral, then it's gonna help speeding up the process a little bit, okay? And so now you have seen through example 4 earlier that, and then we also threw out that generalization. So here I can just quickly recap. For now, in order to use the Riemann sum, okay, if we're integrating, or if we take an integral over an interval from a to b, we break that down into multiple or n intervals, subintervals specifically. So interval 1 is here, interval 1, interval 2, interval 3, and there are many more. Okay, so we are, and then so of course delta x is famously b minus a over n. We can't argue anything about that. Okay, and so about another interval over here, 4th interval, and so on. And then there are many more. Okay, and so the generality that we have found earlier, that the left endpoint at any ith interval is going to be from where our a value is, beginning of the interval. We're going to add with I minus 1 over n. I minus 1 times the delta x. That's what it is. I minus 1 times the delta x. Okay? And so that's a generality to keep right there. I minus 1 times the delta x. And the delta x itself is this expression right here, b minus a, ending point of our integration interval. Subtract the beginning point of our integration interval and divide it by n, the number of subintervals. Okay, so what about the right endpoint in case anyone, or maybe me, in my next example, I might decide to use, out of my own creativity, I might decide to use the right endpoint instead. XR instead of XL here. Okay, then what about right endpoint? Again, same picture here can be reused here. A is the starting point of the overall integration interval. Okay, but now think about, just do a little scratch work right here. For interval number 1, the right endpoint on interval number 1 now is, see, for interval number 1, but the right endpoint is already a plus delta x, because it's the right endpoint. It's the way how it is algebraically. And then the right endpoint on interval number 2, for subinterval number 2 is a but plus 2 times delta x. And then the right endpoint on our 3rd interval, see, the 3rd interval is here, the right endpoint, 3rd interval is here, the right endpoint is right there. So from A is 1 space, 1 delta x to the right, 2 delta x to the right, and 3 delta x to the right. And that's why it's a plus 3 times delta x. And that's how, so now at this point, or how about one more step further, in the 4th interval, okay, the right endpoint is going to be a plus 4 times the delta x. And so now, generally looking, we're seeing that at any ith interval, okay, the right endpoint. So the right endpoint on any ith interval is basically our starting of the overall interval, but plus I times. See, the number. You can see that the multiple of delta x now is always consistent with the position of our current interval. See, it's a 2 delta x. So here is the number 2 interval. Okay, 3 delta x, it's going to be the third interval. So now it's a plus I times the delta I. All right. So now I can write down that generality right here. Okay. And so to keep this lecture somehow, not too lengthy, talking about definite integral in a formal calculus is always a lengthy discussion because, a lot of details need to be brought in and to build your foundation on that. Okay, so we have talked about the midpoint. I would like to save this for viewers and students of mine to find out right here. Midpoint on any ith interval. You can come up with a rule on your own right there. But it is entirely possible. It just allow me not to deliver that here in this lesson right there. Okay, so now once we come up with that generality right here, regulating the left endpoint and the right endpoint, right, as a general way, as a general rule to regulate, to come up with a quick formula for left endpoint and right endpoint at any ith interval. It will help a lot into our next example. Okay, and so now, how about this time allow me to start writing down the next example in the other space. So now we are at example 5 right here. Okay, and example 5 really is exactly the same like example 4. It's a different function and with a different integral. The interval of integration, okay, with different integral limits, that's all. But it's going to be the exact same instruction for the problem. So I want to evaluate, okay, we want to evaluate the integrals we have here is from, it's a x squared plus 4x minus 5, okay, dx. And then we're integrating from minus 5 to 1. Okay, and so, and of course, with this work right here, we want to evaluate this, come up with it, and I mean the exact answer using the limits or the limits definition. Okay, using the limit definition, but I mean the limit on the Riemann sum. As a definition, but it runs through a limit on a Riemann sum. It's a process, and we can use that limit definition to calculate our work right there, to calculate our integral. Okay? All right, so now in this problem right here, clearly speaking, and as a little bit of scratch work, our function f of x in this case is not the simple x squared function anymore. It got x squared plus 4x minus 5. That's something to catch your attention. And so now we can start nailing down a couple of things right here. So our interval of integration runs from, or our integral limits go from -5 to 1. We're accumulating functions heights and striped areas from -5 to 1. Okay, so that means when we're setting up into our Riemann sum, the delta x here needs to be 1 is the ending of our overall interval, and I'm going to subtract -5, and I'm dividing by generally n. And I'm dividing that by generally n. And so delta x here already had a given expression here. Now it's 6 over n. Okay, it's 6 over n. And so now, let's stay with, again, I'm using the plan here. The plan here is, again, I'm using left endpoints. Or how about, you know what, let's change pace right here. left endpoint or using right endpoint will arrive at the exact same answer. Okay, and so here let's say using right endpoint, and even if I was using the midpoint rule for the midpoint rule Riemann sum, it's still going to give me the exact same answer as well. Okay, so right endpoint. All right, so hopefully making it clear like that. Using right endpoint. So we had a little bit taste that in the earlier example problem, it was left endpoint that we apply, and that could have also been done using the right endpoint. And so here I decide to switch to that to give viewers and students of mine, a little bit of experience in various different situations out there. Okay, so right endpoint. So that's the goal. But now allow me to sadly erase this, even though I wrote it here not too long. Okay, so that I have enough space to carry through the whole problem. So now, in this way, just now I clearly stated that I want to use a right endpoint. So in that way, the regulation here say in any ith subinterval, right endpoint in our case here is going to be, see, starting point of the interval is a -5. Okay, and then the general rule to regulate any right endpoint at any ith interval is going to be a, the starting point of the overall interval, plus I times of the delta x spaces over. Okay, so in that way, it's going to be -5 plus I times delta x. Okay, and so now specifically into this problem of ours, we already had an expression, a final expression for delta x. Go ahead and substitute it in. So XR in the ith right endpoint in the ith interval, any ith interval is going to be -5 plus 6 over n, that's delta x, times I, or you can write it as 6i over n. I even highly recommend to write, I recommend my students to write as following, and I will use this final even more simplified form. I'm going to make common denominator and all that and put all this here into one fraction to keep life a little simpler for us. Okay. So here I'm looking at -5n plus 6i over n. All right, so that's my work right here. That's what I'm doing with each of my right endpoint at any ith interval. Okay, so now with all that information, let's shorten it down. So now I'm going to go ahead and set up my integral. So the integral at start from -5 to 1, it's the definite integral from -5 to 1, x squared plus 4x minus 5 dx. Okay, this is going to be equal to, and as an indication, let's write down the indication. We want to go with the right endpoint, so it's the function at the right endpoint on any ith subinterval. Okay, and multiply with delta x. Okay, and then so just produce that start. It never hurt to produce that starting Riemann sum setup like that, so that it can remind people, it can remind us about what we need to do. And then ultimately on top of the Riemann sum work, it's a limit work. Okay, and so now continuing from that step, so now our function here is this lengthy one where each xr sub I right here is given in this expression. Okay, so now I'm looking at as a limit, all right, and growing to infinity. All right, and now it's a summation from I from 1 to n, and now we're looking at minus 5n plus 6i over n. Okay, all square, because that first term here is squared. Okay, plus 4 times, and now minus 5n plus 6i all over n. Okay, and then now I can start erasing all this to make more space for myself. Okay, and then minus 5, and all of that there multiply with the delta x being 6 over n. 6 over n. All right, so I can already skipped a lot of explanation here. Just directly substitute our right endpoint into the place of our function. That's how we produce this lengthy thing like that. Okay, and then from that point on, I am going to have okay, and I'm going to eventually pull out. And so at this point, we're going to start working on the algebra of that. All right, and so in my next step, I am going to factor out the expression 6 over n to be the common factor of my sum. And so it's still a limit problem, letting n increase to infinity. But we're looking at 6 over n times with the summation from I equals 1 to n of all of those minus 5n plus 6i over n all squared plus 4 times and then minus 5n plus 6i over n and minus 5. Okay, and so quickly I'm going to swing back to the other board to explain that the reason I can pull out this 6 over n here, because from the previous step it was part of each of our summation term here. However, as I have explained in my other video lecture, when we specifically worked to train our skill on the operation with summation, then I was explaining that this factor here is indeed the part independent with the ith position of any of our ith term like that. So in that case, and that is the reason why I can now successfully pull out that 6 over n in front, and then I will continue doing that for a few other occasions throughout this problem here. But so now I'm going to quickly point out a little bit of scratch work right here. But this first term inside of our summation term right here, so the summation term has 3 terms in it. So the first term itself, we can think of that as a minus 5n plus 6i squared over n squared. I purposely tear that overall square into, I purposely distributed the square to 2 parts, the numerator and the denominator of our fraction there. Okay, and so this term here, there's no power, but you can think of that as a minus 5n plus 6i over n. Okay, and then with a 4 times in front. Okay, and then minus 5. So now, obviously, with 3 separate terms like that, then I'm going to start, allow me to start being a little skippy in the algebra. So it's all the algebra that explains for this. So you can, if you are my student studying directly with me, you can find me to clarify the algebra that I'm using here. But for public viewers, you can find a way to get a hold of me for algebra clarification. But the skills here are just the common algebra step. We're making the common denominator here. So I'm going to make the common denominator here for all these 3 terms. And I have explained that the first term can be written in this form right here. All right, so now, so for my 3 terms inside of my summation term right here, I can write it as the following. So it's a summation, okay, and let's open those square brackets again. But what I'm looking at now is that I'm going to have minus 5n plus 6i squared plus, and then 4 times minus 5n plus 6i times n. Okay, and then minus 5n squared. This is up, and then all over 1 common denominator, n squared. And this is what happens after I made common denominator and bring all 3 terms, including fractions, into one overall fraction right there. And yes, this is 1 term now of our summation, running from 1 to n. And of course, in front of that sum, we multiply with a common factor of 6 over n. And yes, the problem is still a limit problem, letting n grow to infinity. And yes, so this step here, algebraically, this expression here, this summation here, algebraically equals exactly the other expression above. Okay, and so now at this point, I'm start seeing another. See, so the over n square right here can be regarded as a 1 over n square multiplied with all that, multiplied with the entire ugly-looking thing here. That's the minus 5n plus 6i all square, okay, plus 4n times a minus 5n plus 6i and all that, etc., etc. Okay, 5n squared. Okay, so that fraction here can be seen as that part. And so again, I notice further that this 1 over n squared right here is independent, is the another part independent with the ith position of our term, summation terms. And so in that way, again, I am going to bring that in front in the next step to be and to combine together with this current common factor of ours in front of the Riemann, in front of the sum like that. And so in my next step, the summation is going to become the following. So pulling out the extra 1 over n squared here, I'm going to produce limits n growing to infinity. Okay. And approaching infinity. But now the common factor in front now will be 6 over n cubed. Okay. And then we're going to multiply with the lengthy sum, the summation from 1 to n for all the minus 5n plus 6i square, and then plus, and then yes, now I have my reason to, my right to put the n here together with the 4 in front. So 4n times minus 5n plus 6i, okay, minus 5n squared. And the way how I'm approaching that, how I'm approaching things algebraically here is not the only way. So maybe there are viewers and students who can approach with even less steps than mine. Okay, and less steps, I mean, we don't skip anything, but here I only skip the details, a little bit of details like that. Okay, but then there could be other ways that runs even more efficient than how I'm doing it here. But right now we are mostly just working on the algebra. So in the next step, my plan now is to FOIL out and distribute out each of these, so to get rid of the sub parentheses here. Okay, especially we had that square there. So in my next step, the 6 over n cubed remains exactly the same in front of our summation. Okay, and the first square, and yes, the sum here runs from 1 to n here. The first square gives me, so that becomes a positive 25n squared. Again, check with your algebra to understand how I got that 25n squared right there. And then it's going to be a minus 60ni. Okay, so I just simply think of that as a minus 5n plus 6i times another exact factor like that, and then FOIL out. And that's what I'm consequently ending up with. And then plus a 36i squared. So that's what gives me, after successfully FOILed out that square. And then now I'm going to combine terms with that. So first we need to distribute the 4n right here. So 4n times minus 5n gives me a minus 20n, and actually it's 20n squared here. And then plus another, so plus here is, it's 24ni. Okay, and then minus 20. Actually here we don't, that's the end of our distribution here, and so here it's still only a minus 5n squared right here. But now we got, so now at least up to this point right here, we are ready to start seeing some really nice cancellations, like, you know, opposite terms to be canceled away. Okay, and so you can see that the 25n squared, okay, will cancel perfectly with the 20n squared and the 5n squared together. Okay, 36i squared has nothing to cancel with that, but minus 60ni and then plus 24ni right here can be combined together. Okay, so in my next step, now I'm running a little narrow space here, so forgive me if it's becoming a little hard to see, but in my next space, it's supposed to equal. Okay, and I don't have to start all the way from the left side of my board here, but it's limits as n growing to positive infinity. And now let's look at how surprised our sum becomes here. It's a very, you know, surprising thing here that for this summation from 1 to n, we're looking at, now the first term remains here is a 36i squared. And then now combining the two like terms here, we're looking at minus 36ni. That's another minus 36ni. So it's now surprisingly short, a lot shortened. Okay, but now I do need to get back on my other board to complete out with our steps like that. All right, so now I'm ready to erase all these away, but I don't think I need to. Erase completely here. So let's leave the main part of the problem there. Okay, and so now I'm going to draw a line. And so from our very recent step right there, so at this most recent step right here, then we can now see that according to the work we have seen, according to our learning about summation, and now this current summation has two subterms. So now I can, in my next step, I am going to break it down into two separate terms like that. Okay, two separate summations actually. And so now I'm looking at it's a limit problem. It's a limit problem, letting n grow to infinity. But now I'm looking at and let's produce an overall brackets here. 6n cubed times the first summation here being the 36 I squared summation. Okay, and n and I running from 1 to n. Okay, and then again for the next summation, I break it down, and you see I broke down the two terms, and at the same time I distributed that common factor 6 over n cubed. 6 over n cubed right there. So that's the little steps that I skipped right there that I could have done, you know, keeping that in front and then break that down into two separate summations and then to show another step that distribute out. But I sort of combine two steps together. Okay, and so here it's another, so it's minus, and now it's 6 over n cubed. Okay, as a common factor, but multiply with the summation from 1 to n for the 36 ni. Okay, so for the 36 ni. And so now you can see that each one of these terms here, we still have a little bit of a factor that is independent, right? A little bit of the part that's independent with the ith position. So we can still, even so, let me underline that here with the red ink right here, with the marker right here. But that part right here is still independent with the I, and that part right here is still independent with the I right there. Okay, and so let's take full advantages of those, the components that's independent with the I right there. Okay, so now that means in my next step, I'm going to produce the following. Okay, so I'm going to factor in for my first summation, I am going to factor out the 36 together with that common factor 6 over n cubed. So that gives me 216 over n cubed times the summation of the I squared term. Okay, and summing from 1 to n. Okay, so that's one term that I have right there. And so for my next term, okay, so 36n I'm going to pull out completely and multiply together with that 6 over n cubed. So that gives me, again, 216. But now as we multiply n with this, then it's going to cancel the n with the n cubed right here. So we consequently end up with 216 over n squared here. Okay, and multiply with the summation from 1 to n on just simply the I term. All right, so now each of these, so allow me to put it down as a with red marker again, but each of these summation individually that I put in, I put with a red square bracket underneath right there. Then each one of these is already recognized to be, so we have a quick final expression of this summation in terms of n, and we already learned that, and we also have also already learned a final expression in terms of n for this summation of the simple I term right there. Okay, so what it does for us now, what it means now is that, and allow me to write it in a little bit narrower so that I can still have a little bit space for my next step right there. So in my next step, I'm looking at as a limit, okay, and approaching infinity, okay. But then my first term, so let's still use a bracket here. My first term here gives me, so it's a 216 divided by n cubed, but it's multiplied with the summation becomes n times n plus 1 times I changed my mind. Let's write it at the bottom line so that we have enough space to write. Okay, and so here it's a limit, okay, and growing to infinity, and then I'm using brackets here. So 216 over n cubed is here, okay, but the summation of the I squared term becomes n times n plus 1 times 2n plus 1. and divided by 6. And then, so that takes care of, the whole summation on the I squared terms becomes that fraction, and then the 216 over n cubed is still here. So some more algebra will cancel out nicely in the next step. Okay, and then minus, and now we have 216 over n squared, and we're multiplying that with, so the summation of the I terms will arrive at the final expression n times n plus 1 over 2. Okay, over 2. All right. And so now a lot of nice cancellation can happen right here. I once again need to move on to my other board. So let's quickly clear out the board right there. All right, so what I have now in the next step is going to be limits of n as n goes to infinity. First term becomes 36 times n plus 1 times 2n plus 1. Okay, but all of that is over n squared. Okay, and the next term becomes minus 108, okay, times n plus 1 over n. Okay, and so how did I get to these two shortened terms right here, these two simplified terms? So simply because, again, if we're looking back at this other board from earlier, then in the first term in the brackets here, yes, 216 cancel with 6, okay, and gives me a factor of 36 remains. Okay, and then this n right here cancel with the n cubed right here and gives us an n squared that remains. Okay, and then the 216 cancel with that 2 right there to give us a 1008, and then the n here cancel with the n squared to give me an additional, a remaining n factor at the bottom. And that's how I had that answer. That's how I had that next step on this board right here. Okay, and so now at this point, we can optionally go further with the combined like terms and all that, but I see that we are now ready to take the final limits here. So yes, again, limit laws that we have learned from differential calculus, or a lot of times people call that the Calc 1, from Calculus 1. Then the limit laws allow us to take this as two separate limits from, both going to infinity. And so as we take limits as n grow to increased to infinity, on the first term here, then we're going to end up with, you see, even though it's in factor form, but in the end, I expect that the numerator here is a polynomial of degree 2. And the overall leading coefficient must be a 72 due to the fact that 36 will eventually multiply with that 2 right there and multiply with this n. So it's going to be 72 n squared in the numerator. And so it's equal degree, right? And the leading coefficient in the numerator has to be a 72 for the leading coefficient being the n squared, so it's 72 n squared. So that means that taking this limit right here, we've learned that shortcut trick from Calculus 1, from differential calculus, that this first term will become a positive 72. Okay, so that's the part also that you have to allow me to skip all that explanation from differential calculus right there. I assume that anyone viewing this video already fluent with that skill. Now I'm going to subtract, and then taking the limits as n increase to infinity on this term right here. See, we can have our choice to distribute out the 108, but so think about in the long run, as a consequence of that, then we have the leading coefficient on the top here as a minus 108 n. Okay, so minus 108 is the leading coefficient, and it's the same degree top and bottom here again. So now it's going to be just minus 108. So 72 minus 108. Now it's a simple calculation. It's minus 36. Okay, and so what does that mean there? This is our final work of the Riemann sum and we spent a lot of algebra steps, but our Riemann sum and after taking limits as n grow to infinity on our Riemann sum, we came to minus 36. So that means this answer here because remember we purposely set this up as an integral, a definite integral problem, but we want to evaluate the exact final answer using the Riemann sum, and this is still some part of that work along the way right there. But so in the end, after all that lengthy work and so many steps right there, we arrive at minus 36 to be precise. Okay, and so that's how we had another problem where we really did the accumulation work by going through the limit process that we apply on the Riemann sum like that. So in the end, the point to be nailed down here is that any definite integral is accumulation, where we first had to produce the Riemann sum, and then on top of the Riemann sum, we're going to apply the limit, allow n to grow to infinity. And then from there, we're going to start being able to evaluate and eventually come down to the final answer. Okay.